All right, so here's what we have left. So we have work and energy. These two go together. There's about 8 days, which will put us kind of the middle of September. Excuse me, middle of December. Middle of December. Yeah, way back. Kind of middle of that first week of December for the test. So we'll have definitely a test over work and energy. Then we'll see how the timing, where we're at. We need to do some thermodynamic stuff. We need to do some gas laws, but from a physics perspective, not a chemistry perspective. Some thermodynamics, some buoyancy, kind of some odds and ends, catch-all things. So I know here's how the last 5 days will play out. So last 5 days before we leave for Christmas break, the last day before will be the review for the written final, which will be that Friday. And then after that, you've got a 3-day lab final. So that's how the last 5 days will play out. Review, written final, and that written final was summative from day one, and then you got a 3-day lab final. And I set up the lab final to be kind of a cool summation of everything that we've done. And it's a little bit stressful, but it isn't something where it's going to take you a huge amount of time outside of class to work on, okay? So I don't want to add a tremendous amount to that stress level. But it will be done, but it will be due at the end of the class on that Wednesday, okay? Not after Christmas break, not, maybe later, okay? That's when that's going to be due. All right, so let's talk about work. So when you talk about work from a physics perspective, go away.
Garfield?
Random things show up. So, work from a physics perspective requires two things. You have to have a force, and that force, unlike my pen, has to exert a force through a distance. So work by itself is a pretty simple formula. It's force times the distance. So here's the deal. So let's say that, hand me that block. Thank you. So I've got this block, I pull it across my hand, and I do work because I'm exerting a force through a distance. Now, if I just hold the block like this, I'm not doing any work because I'm exerting a force upward to counteract the pull of gravity, but there's no movement in the direction of that force. Now, if I lift it up, I do work. If I lower it down, I do negative work. And work can be positive or negative depending upon the situation. So here's the simplest calculations you can get. So I'm going to pull this block along at a constant velocity, and I'm going to measure how much force it takes. So here's this block. Here's my force applied. Let's make that simple. Let's say that that's 1 Newton. And let's say that I pulled this thing for a half a meter. So I'm going to exert a 1 Newton force, and I'm going to pull that thing a half a meter. Now, there's gravity acting on it. There's a normal force acting on it. There's a frictional force acting on it, okay? There's all these different forces. But when you're talking about work being done on the block, okay, a lot of work is the preposition, okay? So you talk about work being done on the block, or you talk about work being done by your hand pulling the block. So here's their general rule. If your force is in the direction of motion, or if you're lifting something up, that work is positive. If the work is in the opposite direction of motion, or you lower something down, work is a negative value. Okay, so it can be positive or negative depending upon the situation. But there's always two criteria that have to be met. You have to exert a force, and there has to be movement in the direction of that force. So this is why when I pull this block, yeah, gravity is pulling it down, My hand is provided the normal force, but I won't worry about those in terms of my work calculation because I'm not moving in that direction, okay? That's why they're there, but I don't care about them in terms of work. So in terms of this calculation, all I'm going to do is I'm going to take 1 Newton. I want to multiply that by ½ meter, and I'm going to get 0.50, and there's 2 ways you can write this. One option is that you can write it as Newton meters, okay? It's not newtons per meter, it's just Newton meters. Boom, there you go. Now, the other thing that you'll see is that energy and work are 2 sides of the same coin. So all types of energy, which we'll spend more time talking about after we get back, but all types of energy are measured in what units, for those of you that have been through chemistry? Joules. Joules. Okay, and this isn't what you're going to get like at, Zales or something. So this was named after...
like the gas station.
Huh? Okay. So this is named after Prescott Joule. Prescott Joule was pretty popular in high school because his family had a brewery. It's like, oh, party at Prescott's cool, okay? And so Prescott was the first one to come up with the idea that mechanical energy and thermal energy are related. So what he did is he took like a very, very well-sealed container, and he had water in there, and he had like a baffle system. So if you've ever seen like the machines that make like homemade ice cream, there's like a shaft that goes in there and these baffles that turn to stir everything. And what he did is that he had a rope tied around that, and that rope was tied to a pulley, and that was tied to a weight. And so what he did is that he dropped the weight, and as the weight fell, it made those baffles inside the container of water move. And they would spin, they would agitate the water. And what he realized is that there was a direct relationship between how much potential energy there was holding this thing up and letting it fall, and then an increase in the thermal energy within the system. Now, you all intuitively understand this. Let's say, for example, I have 2 identical containers, both full of, say, ice, all right? One, I just let sit there. I'm just going to sit there, boom, that's all we're going to do. The other one, I'm going to sit here and I'm going to shake it up like this. Which one's going to melt faster? The one that's just sitting here, or the one where there's motion? Yeah, the one with motion, right? So I'm doing work. I'm agitating that ice. I'm introducing kinetic energy into that system. So he was the first one that quantified that relationship between the weight of that falling mass and that increase in temperature within the system. So if there's one unifying theme that unites all branches of science, whether it's geology, biology, chemistry, physics, astronomy, doesn't make any difference. The one unifying...
It was a good one, too. It's a raisin.
Oh, there's no good raisins.
I love raisins.
No, there are no good
is.
raisins.
There's big ones, though.
There's good chocolate-covered raisins, but raisins in themselves, yeah. And certainly raisins in cookies are an abomination.
No, oh, the raisin cookies are so good.
Oh, no, skip it. This is not open for discussion.
Okay.
Not open for discussion. Okay, so whether it's in your biology class and you're studying ADP and ATP, or if you're in a chemistry class and you're studying thermochemistry, if you're in a physics class and you're studying work and potential energy and kinetic energy, that's the one unifying thing. Is there's one thing that balances across all branches of science, and that's energy. Okay, so let's look at a couple of examples. So let's say that I take this rubber stopper and I lift it up like this. So when I lift it up like this, did I just do work?
Yes.
Yes, why?
Distance and force.
Yeah, I exerted the force over distance, right? If I lift it up, I did work. But if I just hold it like this, am I doing work? No. I'm exerting a force. My arm is going to get tired, but I'm not doing any work. Okay? Now, what if I walk along and I carry the rubber stopper like this?
I don't think
Am
so.
I doing work?
Yes.
Are you?
Wait,
No? Yeah, the force is not going in a distance.
Because the force I'm exerting is lifting it up. Now, I had to do a tiny bit of work to get it to move. Okay? Because I had to exert a little bit of force in the direction, because otherwise, it's like if this was the magic frictionless stopper, and my hand was frictionless, then I go to move my hand, what would the stopper do? Yeah, I just go, whoink, okay? It would just stay in place. So I had to do a little bit of work to get it to move, but generally not. Even if I put this block on top of my head, and I walk like this, okay, am I doing work?
No.
No, because what's the direction of motion? Yeah, the direction of motion is
Opposite of the force.
horizontal,
Or not opposite.
but the force that I'm exerting on it is upward. Now, what if I take a rubber stopper, and once I get it up to speed, obviously I had to do work to get it moving. Well, once I get it up to speed, am I doing work?
no,
Why not?
because you're not exerting a force.
Yeah.
I'm exerting a force.
But it's not you that's exerting the force, I don't
It's
think,
the
right?
centripetal
It's the
force.
centripetal force, I thought. Maybe I'm wrong.
That's
Actually,
caused by
Okay,
it's caused by the string.
Wait, maybe that's the way
but if I let go of it,
I'm not a physicist.
what's it going to do?
it's gonna fly.
It's going to go flying off.
Does that mean you're doing work?
Yeah, no. It means I'm exerting a force.
Okay.
Okay? There's a big difference. So here's the rubber stopper. What's the direction of the force that I'm exerting to keep it moving in a circle? Inward. At a right angle to the...
Velocity vector.
So, but was there any displacement in that direction?
No.
No. Because there's no displacement in that direction, I'm not doing any work. Okay?
Well, I'm
Got that idea?
No, not really. What do you mean, like displacement?
So,
I get it.
now, hold on.
Because the distance has to be in the direction of the force, like
Hold on.
not just of the.
Now, if I do this, when I get it going over my head, and then I have it wrap around my finger, then I would be doing work.
Yeah.
Because there would be a force and it would be moving in the direction of that force. Because you have to have two things. You have to have a force and there has to be movement in the direction of that force. So if I just swing this thing around, okay,
So since it's not going in.
yeah,
in
there's
with
no
the-
change in the radius of that swing.
Okay, that makes sense. Yeah.
Okay? Now, sometimes work can be negative. So let's go back to the block. So if I'm pulling that block at a constant velocity, what's the only reason I have to keep applying a force? Because there is friction. There's an opposing force of friction, right? So if my applied force is 1 Newton, what's the value of my frictional force? Do not make this difficult.
-1.
-1 Newton, right? I'm pulling it at a constant velocity. True?
Yes.
So as I pull this thing, I have an applied force of 1 Newton. So there's my force applied. So my force friction is going to be -1 Newton. Now, let's talk about this concept. It's cold outside, okay? And you go out and you're waiting and you've lost your mittens, okay? So what are you going to do to warm up your hands? You're going to do this, right?
Yes.
Now, when you do that, are you doing work?
Yes.
Yes, you're exerting a force over a
Distance.
distance. Because if you just do this, you look very angelic, right? But you're really not going to warm your hands up, okay? And if you do this, okay, it's not very effective either. What are you doing? Trying to warm up your hands. Oh, you flunked physics, didn't you? Okay, but if you do this, right, then you're doing work. So what are you fundamentally generating when you do this? Energy, right? You're generating thermal energy. So those little particles or atoms that make up your hand when you do this, they go, oh, this is weird, right? And they kind of flip out and they start vibrating, okay? And you feel that as thermal energy because it doesn't like that. So when you're doing this, you're making the atoms that make up your hand vibrate in a way that they don't like to. And they go, their way of voicing their displeasure is they're going to give off thermal energy. And that's what you're going to feel in your hands plus one, okay? So anytime there's friction, there's heat being generated, okay? Every time there's friction, there's going to be heat. So when I pull this block across the table, there's a little bit of thermal energy that's being generated, okay? Not very much. It isn't like I do this and all of a sudden my papers catch on fire. It's like, wow, brilliant. That was a lot of thermal energy. But if you've ever seen any of the survival shows, okay, people are out in the middle of nowhere, they're trying to start a fire. What do?
Bang two rocks together.
Okay, that's a possibility. If you have flint, you bang that together. Are you doing work when you do that?
Yeah.
You're exerting a force over a distance, right? Or what's the other option you can do?
A little one sticks together.
Yeah.
Oh.
Rub 2 sticks together, okay? Or you take like a dry piece of wood and you wallow it out and you put a stick in there and you rub that back and forth, okay? Again, are you doing work? Yes, and you're transferring kinetic energy of your hands into the thermal energy here. Now, if you just put the stick down, are you going to start a fire? No. Okay? It's like, oh, come on. Okay? No, you're not going to get anywhere. But if you rub that stick and you generate, and you do enough work and you generate enough thermal energy, you can start a fire. So, how we account for thermal energy from a work perspective. So if we want to calculate how much work is done in overcoming friction, we're going to do the exact same equation of force times distance. But now I'm going to use a negative 1 Newton, because that's in the opposite direction of motion. I'm going to multiply that by a half a meter, and I would get negative 0.5 joules. So that's the work done in overcoming friction, okay? But the work done in pulling the block would be a positive 0.5 joules. So if you're at a constant velocity, the work that's done in overcoming friction, which is going to generate a little bit of heat. So when I pull this across here, I am generating a little bit of heat, okay? Not enough to, oh, my house is cold, let me pull a block across a table, okay? No. But you are going to generate a little bit of thermal energy, and that's how we account for that. Now, if this was the magic frictionless block, and this was the magic frictionless table, okay? Magic frictionless block, magic frictionless table. I give it a push. Would I have to do work to keep the block moving? No, why not?
No other forces.
Yeah,
An
there's no
object in
frictional
motion
force
will
to
stay in
overcome.
motion.
So now, would I have to do work to make it move? Yes. But I wouldn't have to do work to keep it moving because there's no frictional force to be opposed. So therefore, the inertia will just keep it moving. So if it's frictionless, I don't have to do any work. Now, is gravity acting on it? Yeah. Is there a normal force? Yeah. Don't care about them because they're not in the direction of motion. Got that idea? Okay. Now, let's say I do this action. So I'm going to take the block, I'm going to pull it, but instead of pulling it horizontally, now I'm going to pull it using a string, but the string's going to be at an angle. Okay? So visualize this. I'm pulling the string, but the string's at an angle. So what are all of the forces? So here's this block. Here's the string that's being pulled up like this. So what are all of the forces acting on this system?
Normal.
Normal force. Okay.
Gravity.
Got that. What else?
Gravity.
Gravity. Got that.
Did you say frictionless?
No, 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 no. It is, if it was frictionless, it would be accelerating.
Oh yeah. So friction
So there's some friction, okay?
applied. Right?
Yeah? We'll call that the tension. Okay? Right? So we're like this, okay? Going it like this, right? Okay? Now, within that tension, are there some components of that tension? Maybe the X component and the Y component. Now, out of 1, 2, 3, 4, 5, 6, out of those 6 vectors that represent forces, what's the only one that I'm going to use in calculating work done in moving the block? What did you say, Nikki B?
FX,
Why?
because it's the only force acting in the direction.
Yeah. This is the only force that's acting in the direction of motion. Okay? Is there gravity? Yeah. Is there normal? Yeah. Is there friction? Yeah. Okay? Doesn't make any difference. The only one that I consider when you do work, listen to me very carefully. When you're doing work calculations, it is only the force in the direction of motion. And you draw that vector and you go, wow, which one is in the direction of motion? And it's exactly what Nick said. The only force that's in the direction of motion is the horizontal component of that velocity. Is there tension? Yeah. But that isn't the direction that the block is moving. Okay? So since the block is moving this way, it's only that force that I'm going to worry about. Got that idea? Now, if I wanted to calculate the work done in overcoming friction, I would take that force friction, which would be equal and opposite to that Fx value, and I'm going to multiply that by the distance. Okay? Because that's the work that's done in overcoming friction. All right, so let's play out this scenario. So, next August, you're all excited, you're moving off to college. Woo! Okay? So, here's the truck. Okay? And we'll flame it.
It's like a boat.
Okay?
That's the hatchback.
And, yeah, there you go.
Oh.
And so you've got a refrigerator,
Whatever they're called.
little dorm-sized refrigerator, and it has a mass of 10 kilograms, okay? And you need to lift that to a height of 1 meter. Get it into the back of the truck, okay? So 1 meter, about like yay, right? It's a 10 kilogram refrigerator. You're gonna grab it, lift it up, boom, got it, set. Are you gonna do work?
Yes.
How much work are you gonna do?
Whatever distance times force.
1 times however much force.
Oh, you have to calculate the force probably.
1 times 10?
10 times
Times 9.8.
9.8.
10 joules?
Oh.
No,
You have to-
No.
How do you calculate joules?
No,
because it's
No.
force times distance.
it's not 10 joules.
It's
Why is it
newtons.
not 10 joules?
Because it's
not
Energy.
the
It's not
force.
energy.
Energy is Newton meters force times distance. So when you lift something, it's the weight of the block. Okay?
Yes.
It isn't the mass, it's the weight. So like if I take, for example, a 1 kilogram mass, which I happen to have handy. Got a 1 kilogram mass. I lift it to a height of 1 meter. Okay? Lift it to a height of 1 meter. How much force do I have to exert? 9.8 newtons, right? Because that's the weight that I have to overcome.
See,
And I lift it up to a height of 1 meter, I would do 9.8 joules of work. So if I lift it up to a height of 1 meter, that's roughly about 10 joules. Okay? If I lower it down, I would do negative 10 joules of work because I'm lowering it back down. Because if you think about it, when you lower something down, the force that you're exerting is upward, but your motion is downward. So when you lower something down, it's like you're going in the opposite direction that it wants to. So that would be negative value. You lift it up, oh, it's going in this direction. That's the direction of that force, so I would do positive work. So whenever you lift something up, it's positive work. You lower something down, it's negative work. Okay? So, let's go back to this question. How much work do I do in lifting a 10 kilogram refrigerator up to the bed of that truck?
98.
98?
90.
Yeah.
98?
I think.
Because check my math, but 10 times 9.8 meters per second squared gets you 98 newtons times 1 meter, which is going to get you 98 joules. Now here's an interesting concept. Oh, let's talk about a force distance graph. So I exerted a force of 98 newtons over a distance of 1 meter. Ooh, that looks like a rectangle. How do you find the area of a rectangle? Based on its height. So what do you think the area on a force distance graph gives you?
Probably the joules, the work.
Work. So the area on a force distance graph gets you Newton meters, which is the same thing as joules, which is the same thing as work. Now, if it was a force time graph, what would that give you?
Force times time is change in momentum.
Yes. So if it's a force time graph, you get change in momentum. If it's a force distance graph, you get work. Okay? Related, but certainly not the same thing. Now, let's say that you're here trying to get the refrigerator in the back of the truck. And you're going, man, 98 newtons, that's a lot. It's not feeling it. But, conveniently, you happen to have the magic frictionless ramp. How cool is that? Frictionless. Okay? And let's say that that ramp is 2 meters long. Doing some simple trig, that means that forms an angle of 30 degrees. Okay? So you obviously can't push it up because it's frictionless. So you're going to stand here in the bed of the truck with a rope, and you're going to pull the refrigerator up the magic frictionless inclined plane. Okay? So here's your two options. You can grab the refrigerator and go, hooah, bam, set it up there. It's an option. Option number two, you're cool. Hey, I got the magic frictionless ramp. I'm just going to stand at the truck, pull it up. In which situation are you going to do more work? Lifting it up or using the ramp?
Lifting it up.
I
Why?
like the ramp.
Because using the ramp, it's force parallel instead of force gravity, and force parallel will be less.
Ah,
Ah.
maybe.
Yeah,
You have to calculate it first.
Well, let's talk about this force parallel thing. And the other thing that you'll see a whole bunch of things that we've talked about before gets all recombined into this last unit. Okay?
This is our last.
So let's just talk about a little force parallel action, shall we? So I got a 2 meter long ramp. That makes that a 30-degree angle because that is 1 meter. And it weighs 98 newtons. There's your FG. So how are you going to calculate your force parallel? FG?
Sine theta.
So my force parallel is going to equal FG sine theta. If I take 98 newtons times the sine of 30 degrees, trust me, you get 49 newtons.
Oh, it's
Oh,
gonna
they
be
equal the same.
Oh, they're going to be the same number.
Yeah.
Okay, because here's the deal.
Oops.
I can either exert a 49 Newton force over 2 meters, or I can exert a 98 Newton force over 1 meter. I'm going to do the exact same amount of work. Okay? Is the ramp easier?
Yeah.
Yes. I'm going to exert less force. Admittedly, that's easier. But what's my trade-off?
A longer time.
No, this has
Like
nothing to do with
distance.
time. This has nothing to do with
My
time.
bad.
Nothing to do with time.
Distance. I would just be like, I feel
You
like
were
it
just
would
seeing if I
take
was
me
paying
longer
attention?
time though.
You were just seeing if I was paying attention.
Yeah.
So, does Burkhamp still have his wits about him? Yeah, it's okay, right? Kind of like that.
Although I was like kind of find it funny that it's only 10 kilograms. That's only 20 pounds.
It's a small refrigerator.
I know, but I was like, oh,
It
they
makes-
were like, oh, this thing's so heavy, and I was like, man. I know it's all like theoretical, but I just find it kind of funny.
Okay. Anyway, back to our story. So, now, in reality, there's not a frictionless inclined plane. In reality, there's going to be some friction. So in reality, instead of 49 newtons, what are you going to have to do? More or less than 49 newtons? More. In reality, you're actually going to do more work because there's going to be friction. So that might be 60 newtons. Okay? But still, 60 newtons is still less than the 98 that it would take just to lift it. So when you're using an inclined plane, you're actually doing more work because you have friction to overcome. Okay. Got that idea. All right. What if we made the ramp even longer?
It's still the same work.
Still the same work as long as it is, but you're still trading that off. Now, it's a similar type of idea with force times time equaling change in momentum. So, option number one, you exert a 98 Newton force over a distance of 1 meter, right? Just lift it up. Boom. Okay? Now, if you use the magic frictionless ramp, what's going to happen? You're going to exert 49 newtons, but you're going to exert that over 2 meters. What do you think is going to be true of those areas?
They're equal.
Areas will be the same, okay? As long as there's no friction. Make the ramp even longer, what's going to happen to the value of that force?
Decrease.
Smaller and smaller and smaller, right? Okay? Got the idea. We're good. Now, let's talk about time.
Okay.
Let's talk about time. It's about time?
Also, I have a question.
Okay.
Cause,
No heckling from the studio audience, that's my job.
but this is work that's being done on the block, and isn't that different than like your work, or is it the same?
You're doing the work on the block.
So there's no work. So it's equal.
There's work done by over friction. If I drop the block, you can talk about the work done by gravity. But we're always going to talk about the work that we're going to do.
So okay. Is it always positive?
As
No.
long as it's going up or in the direction of motion.
Okay.
If it's in the opposite direction of motion or going down, then it's going to be negative work.
Okay.
Okay. Now, so let's talk about power. So there's different ways you could talk about power, but one of the simplest way is that it's work divided by time. So work is going to be measured in joules. Time is going to be measured in seconds. So the units are joules per second. You've also known as watts. Now, where have you all seen watts before?
Batteries.
Huh?
Batteries.
Light bulbs.
How about light bulbs?
Oh yeah.
Bulb came on? Yeah. Yeah. Bulbs.
Per wattage.
So,
Oh, microwaves.
Yeah.
that's
that-
true too, yes. So,
Lightning strikes.
what's going to be brighter? A 60-watt bulb or a 100-watt bulb? 100 watt. Why?
Has more watts, more energy.
There's more energy per unit
Second.
of time. Okay? Right? More energy per unit of time. So let's look at a simple example. I'm going to take a 1 kilogram mass and I'm going to lift it to a height of 1 meter. So I'm going to take this, boom, lift it up to a height of 1 meter. Did I just do work?
Yeah.
I exerted a force through a,
Distance.
how much work did I do? 9.8 joules, right? Because if I take 1 kilogram times G, I get 9.8 newtons. 9.8 newtons times 1 meter gets me
9.8.
9.8 joules. Now, I do this for dramatic effect, and let's say that takes me 2 seconds, okay? So if I want to figure out how much power it takes to lift a 1 kilogram mass to a height of 1 meter in 2 seconds, I'm going to take those 9.8 joules, I'm going to divide that by, and I'm going to get 4.9 watts. Okay? True? Everybody cool with that?
Yes.
Now, I'm a little bit rushed for time. Instead of doing that in 2 seconds, I'm going to go whoop. I'm going to do it in 1 second. Right? Stunning. It was just a silver flash. Okay, that's all you saw. I'm going to do that in 1 second. What's that going to do to the work that I do?
Nothing.
Absolutely nothing. I'm still going to do 9.8 joules of work.
Time doesn't matter.
But what's going to happen to the power requirement?
More power. I mean,
It's going to increase because now instead of dividing it by 2 seconds, now I'm going to divide by. So the faster you do work, the more power that takes. Okay? So remember that if you're vacuuming and parental unit says, God, can you go any slower? And you're going, if I do this work faster, that's going to cost me more power. And I just don't have that. Back off me, okay? Just don't have the power to vacuum quickly today. I'm just not feeling it, okay? And your parents are going, damn education. What are those kids teaching you? What?
So the 4.9 W is the power?
Yes.
we can just write
So what
W
is
for it.
W is the word?
No, W stands for watts.
Oh,
W is short for watts.
Is it a capital or?
Yes, it's capital.
Okay.
Wait, how do you do like power? What's its like letter?
Work is
Is it just P?
So-
joules, I thought.
The variable for power
Variable, that's what
is
it
P.
Just P? Okay.
Yeah. Okay.
Pushing P.
Now, here's the other way that you can look at this, which is a little bit clever. So we just said power is work divided by time, right? Now, you'll see this more on
This is work lower.
Monday, but work also equals a change in energy per unit of time. Okay? That's another way that you can look at this.
Whoa.
Now, the other way that you can look at this
Oh my gosh.
is that work is force times distance, true?
Yeah.
Divided by time. Now, if I take distance and divide that by time, I get, so you can also write power as force times velocity. Now, here's how this plays out. I'm guessing at some point in your lives, you will drive a battery-powered car.
No.
Okay? And if you do, you need to be keenly aware of this equation. Because your batteries only hold so much power. Okay?
Oh yeah.
Right? They only hold so much power. And when you run out, it isn't like, hey, can you take that 5-gallon can and go give me some more power that I can pour into my batteries? Okay?
Charge it.
So you need to be aware of this. Now, let's play out 2 scenarios. Scenario number 1, you're driving down to Oklahoma City, and true Kansas fashion, you're driving into a really strong headwind. Okay? What's going to happen to the force that your car has to exert to drive into that strong headwind? It's going to increase. So what's going to happen to your power consumption? It's going to increase, which means your batteries are going to run out faster if you're driving into a strong headwind. Also, the faster you drive, what's going to happen to your power consumption? It's going to go up. Okay? Now, the contrast to that, let's say you're driving from Oklahoma City back up to Wichita, and you have a strong south wind pushing you. Now what's going to happen to your power consumption? It'll become less because that wind is pushing you along. So if you ever drive a battery-powered car, you remember that your power consumption is force times velocity. Okay? Just remember that. Okay, so stop y'all the camera. Okay, so let me get you started on some of these. So let's talk about number 8, because one of the things we're eventually going to talk about is density.
Ah.
So here's a train.
You see that? Density.
Over velocity.
Bruh.
volume?
What number is this?
Okay? Now, in chemistry, you all learned the formula for density is mass divided by volume. Okay, that's how you learned it. And in chemistry, mass is measured in grams and the volume is going to be in cubic centimeters. Okay? That's the chemistry version of density.
Oh, I
Okay?
heard density.
Now,
Oh yeah.
the physics version of density is rho, which is the Greek letter rho. It's kind of like a jacked up letter P.
It's like a
It's still
lowercase
mass divided by volume, but mass is going to be in kilograms, and the volume is going to be in cubic meters. Okay, so that way we stick true with the MKS system. So density in a chemistry class of water, for example, is 1 gram per cubic centimeter. So 1 gram is like a paper clip. 1 cubic centimeter is about the end of your pinky. So if I give a density lecture in the chemistry classes, density is grams per cubic centimeter, or grams per milliliter if you're talking about a gas or a liquid. In physics, it's always kilograms per cubic meter. So the density of water in a physics class is 1,000 kilograms per cubic meter. So if you have imagine like a cubic centimeter or cubic meter of water, okay, which would be a lot. So within that cubic centimeter of, or cubic meter of water, you would have 1,000 1 kilogram masses, okay? So it's still the same ratio, but the numbers are just a lot bigger. So on problem number 8, here's the setup. You've got the 2.25 times 10 to the third newtons. That's the weight of the bucket just by itself. Okay, that's just the bucket. Now, trains that just lift buckets, and that's all they do, don't sell very well. What does your train do? It lifts an empty bucket. Is that all it does?
Yes.
It's cool. It's a really cool bucket.
I love buckets.
Can you put anything in it? No. It just lifts the bucket. Okay. Probably not going to sell very well. So fundamentally, the train lifts stuff inside the bucket, right? So in this case, we're going to put dirt inside the bucket. And you're going to put 1.15 cubic centimeters of dirt inside the bucket. So you're going to know the volume of dirt inside the bucket. I also gave you the density of dirt, 2,000 kilograms per cubic meter. So that's about twice the density of water. So would this dirt float or sink in the water?
Sink.
Pretty much sink, because it's twice as dense as water. Okay? So you're going to know the density of the soil. You're going to know the volume of the soil. Knowing those two things, what can you find?
The mass of the dirt?
The mass of the dirt.
Ah.
Eventually,
Sam, Sam, no, stop. You can find the mass of the dirt. If you know the mass of the dirt, what can you find then?
The work?
The weight of the dirt.
This is getting worse.
I know, it's really bad. So, think about this. You're going to lift the bucket, and then you're going to lift the dirt that's inside the bucket. So what's the total amount that you're going to lift? The bucket plus the dirt that's inside of it. So you need to take the weight of the bucket and add that to the weight of the dirt. That's the total force that you're going to have. Okay? When you get to number 9, let me give you a visual on number 9. It's going to be just like this. Okay? So here's this block. Megan's walking along, and she's pulling a rope. Now, just to make sure everybody's cool with how this starts. The horizontal force is 462 newtons. So that's 462 newtons right there. That's the force in the horizontal direction. Okay? That's the force in the horizontal direction. Number 9 is not an inclined plane problem. She's walking along, she's dragging the box. It's like this. Number 9 is not an inclined plane problem. There's angles, but it's not an inclined plane problem. So, you want to find the tension in the rope. On part B, you want to find the tension in the rope. Is that tension in the rope going to be bigger or smaller than 462 newtons? Bigger. Okay? Use some trig functions. When you get to number 10, there's 2 ways you can work number 10. You can either take the force parallel of President Biden and multiply that by the length of the escalator, or you can take the weight of President Biden and multiply that by the height that he gets lifted up. It's up to you. When you get to number 12, okay? When you get to number 12, have this visual of what we did with the carts the day before the test, okay? You have the 2 carts. We let go of them. One has more mass, one has smaller mass, okay? And we're going to let them go for the same amount of time. Okay, this is going to be important. They're going to travel for the same amount of time. So if you remember back, here was one with a 50-gram mass. Here was the other one, but it had a mass sitting on top of it. Okay, so this was Nikki B's. That was Stanley B's. Okay? So, if we let them go for the same amount of time, which one traveled further? Mine or Nick's? Mine did.
Yeah.
Okay? Now, keep that in mind. We kept the time the same, but not the distance. Okay? So keep that in mind. We kept the time the same, but not the distance. So, what you want to look at on number 12. So on this one, when I say, which object will travel farther, explain. And then I tell you in big bold letters at the bottom, I say, as part of each answer, you should include an equation to justify your answer. The equation that does not justify your answer is F equals ma. That is not the equation. Okay? You do need to know that because you need to talk about acceleration. But how does a larger acceleration translate into a greater distance? That's what you want to think through. Or how does a greater acceleration translate into a bigger velocity? Or how does that relate to work in terms of distance? Okay? So when you answer 12, you want to give, you can say it's block B, it's block A, it's the same, whatever you think it is. Okay? But make sure that you give a mathematical justification for that answer. Okay, I'm done. You're on your own. Tomorrow we'll talk about Africa, so this is technically going to be due the Monday after Thanksgiving break. So you won't have any homework over Thanksgiving break.
Are we going to go over this tomorrow or Monday?
If you, it's